Right. So if you look at the title, it's a bit well intriguing simply because when Rishad asked Olga whether we can present some demo, Olga say yes, we can present something on visualization or on deep learning with the machine. And then Rishad came with a topic which obliged us to cover both topics actually. Right. So it will be two parts. As I say, two parts on this, and then the first one is let us look at the how it's always intriguing to see how the Tsetlin machine learn data, and we are also taught a lot that it is interpretable. So now let's look how it's interpret uh, the knowledge, and we'll start with this MNIST digital patterns. So here you can see, so if you combine, if you overlap all of the numbers, zeros, 1, 2, 3, so you could see this heat map actually which give you a pattern of the each and every digit in the MNIST data set. And now let us look at how Tsetlin machine can develop these patterns by learning from the digital MNIST. So here on the top, you can see the positive clauses. Positive means that it's what for. So this is how 0 looks like. Yeah, and on the top, you could see the positive clauses. So the positive literal. So it means that this should be 1, pixel should be 1. Here, the red one means that it should be zeros. And then you can see that the patterns are really reassemble what we can see from the heat map when we overlap all of the digits. And then the negative clause means that this is not, for example, this is not 0. So not 0 is when you have 1 in the center. Yeah. So this is definitely not 0. And so again, so you can see the positive and negative clauses. So this heat map again, so this heat map, you can get them when you sum all of the clause outputs. It might be useful to look at each individual clause and see how individual clause looks like. And here again, so here on the left, you can see the aggregated version. Yeah, so it's like a heat map when you simply sum or stack all of the clauses. But here you can see how individual clauses are, how they learn. And what is also intriguing here is that you can see that some of them are quite busy. Yeah, so quite a few includes and of positive or negative literals, but some clauses are barely progressing. For example, if you look at this one, so nothing. So it means that this is redundant. And then if you look at some of them, well, probably not at this stage. So just let me try to, we can get some. Just I want to stop at some point. No, well, it doesn't allow me to stop at now. Anyway, so you can see that some of them are progressing well, some of them are even regressing. So for some of them, you could see that this never happened. For example, it will tell you, well, this is negative clauses. And again, it shows you that what is not 0, yeah? So apparently not 0 is when we have something in the very middle. So when there are positive or when there are ones or black pixel in the middle of the picture, it's, well, still it behave a bit stupid. Can we... Right. So again, so if you look at this example, it's not possible that this is 0, right? Because this green pixel means that this should be 1. It's never 0. So because you can never find an example when 0 is when this pixel is dark. And this means that it's a really collective behavior of learning automaton. The mainstream moving towards getting some knowledge, but some of the clauses might even go to the opposite direction. Yeah, some of them might not be progressing well, but some of them might even be regressing. So this give you, so when you look at each individual clauses, it gives you some important insights that some of the clauses actually can be removed. And by removing some clauses, you can even increase the accuracy of your learning. Some of the clauses probably could be magnified, their influence could be magnified. So you can also increase an accuracy in this way. And so again, so that was a positive clauses, and then we have a negative clauses saying you that this is not zero, for example. So it just visually show you what sort of pattern it produces. And what's also important is that finally, so each of the clauses, we can consider that each clause generate you a rule. Yeah. So it's like if this pixel and that pixel and not that and not this is zero or this is one. So if we consider each clause as a rule, then when we have 100 clauses, it means that 100 rules. 1,000 clauses, 1,000 rules, which is not actually practical because nobody would like to interpret the 1,000 rule. So apparently, we do need to have some post-processing mechanism to post-process clauses and to extract knowledge. And this post-processing could be, by aggregating clauses and then maybe selecting those which are well progressing, which are the most important, then cutting off, do sort of pruning, so cutting off those which are less important or even or badly progressing or even wrong for this particular Tsetlin machine. Right, so that was a summary on the visualization. Now a few words about the deep Tsetlin machine. So it was a few talks even today, and Oli presented yesterday his work on the multi-level Tsetlin machine, and apparently he got some exciting results. So the accuracy jumped considerably from 60-something to 85, if I'm not mistaken. So we explored this approach in parallel, and we want to create sort of a deep oval. We started with a two-layer machine. And the idea is that we train the first layer, then we freeze the Tsetlin automaton of the first layer, and then connect the clause output of the first layer to the inputs of the second layer TM, and then tune the second layer to understand the weaknesses of the first layer TM. And we can do it in a number of cycles. So the general training cycle looks like train first TM, tune the second TM, and then repeat if necessary. So here you can see how it looks like. So after we train the first layer TM, we can cut simply the summation and then the feedback module, freeze the Tsetlin automatons, and then connect the second layer TM directly to the clause output of the first layer TM. So the first layer TM now it's frozen. So all the TA are frozen, and we don't even need those TA. And by the way, those TA can be used as shared resources. So we can reuse them while we are tuning the second layer TM. And then, so in such a way, well, this is the code. And that became possible because Ole recently introduced these transform methods. So the transform methods, actually, it's not documented, and it was introduced recently this year, if I'm not mistaken. So it's a new method that Ole introduced there. Probably he was also trying to experiment with the multi-layer stuff. So if you use this, it will give you a rough clause output, and then you can use this clause output for as an input for the next layer TM. And here you can see the burst in accuracy. So again, the first 100 layer, we train the first layer. Then we freeze the first TM, then start to train to tune the second TM. And then you can see the burst in both in the training and the validation accuracy. If you continue to train, because we also, you can continue to train the first TM for the next 100 epoch, because it will be, it's actually quite natural to compare. What if we train the first layer TM for 200 epoch, or what if we train it for the 100 and then tune the second layer TM for another 100 epoch? And then you can see that this increase is just, well, it's 99 using only 100 of clauses. So it was interesting observations and very promising. Yes, you can reuse the same TA. You can reuse the same TA. Right. So then we try to experiment with what is more promising. Train the first TM for longer, and then tune the second TM for a small number of epoch, or it is more promising, or it get a better result if you train the first layer TM for for 100, for example, for a few number of epoch, and then you train the second layer TM or tune the second layer TM for longer, or when you like tune, train, repeat for like 4,000 of cycles. And apparently, what we found is that when you tune the second layer TM for longer, it will give you high accuracy. So it looks like the second layer TM, it learn in perfectness of the first layer TM and tell you and simply suggest you exactly where the first layer TM fail. And because it's no way it's fail, it give you a high accuracy. So it's pretty similar to what Oli. Yep.
So I understand the training process. What happens to the inference process? Do you use both layers or only one?
Yes, simply for the second layer TM, you use the clause output to the first layer.
So you take that to the...
Yeah, so you need to have both. So you send the rough data to the first layer TM, it produces the clause output, and then you see it to the second layer TM, and then it produces you the final classification.
Every time you train, you store the includes in the register.
Yeah. And it seems that it's very close to what Oli was saying yesterday, when he said that you have a different specialist. But the most important that the specialist know when he doesn't really know. So it looked like the second layer TM give you this capability to know when the first layer TM doesn't really know. And with this additional knowledge, it produces you much greater accuracy.
After some assistant.
Yeah, it looked like, yeah. And then we say that, well, one layer is good. Well, why not two layer give you even better accuracy? Why not to have more layers? Here there is an example with a 5 layer. And here you can see this for training accuracy. You can reach easily, 100%. But then if you look at the validation accuracy, so the validation accuracy starts to degrade. So we have the first jump here, and then it started to degrade. And finally, so it looks like now we see this overfitting stuff, yeah, which probably. So the idea that 2 layers seems to be the optimal here. So one is so the first one produce some result, but the second TM is like a manager or controller of the first TM, and then it learns when the first TM fail, and then it provide, yeah. So it's simply it was just amazing results, and then we believe that this is quite promising, and combined with multimodal sort of learning that Oli promoted yesterday, when he said that, all right, we have the same data, but then we have different Booleanization techniques. So different Booleanization techniques create you sort of a different model knowledge, and then you so you can use them as a first layer TMs work in parallel, but then the second layer TM would combine and learn their imperfectness and give you probably even better accuracy. So what Oli, just to finish, what Oli was, so what we believe we can improve in Oli's approach, he sent to the second layer only clause sum. Yeah, we are sending to the second layer rough clause outputs. Yes, this give you more. By the way, it may be not as dramatic in the, so it increased number of literal, can increase, but it depends on what is your technique, what is your Booleanization technique, because class sum, if it is 255, for example, and then you need to Booleanize them in one-hot encoding, it will give you pretty much the same number of literals. So if you send the clause output rather than clause sum, it might boost your accuracy even further.
Actually, if you combine all those approaches, parallel diverse TMs together with yours, you might see that individually, the individual specialist post hoc TMs will also allow you more validation accuracies, even for problems like C400 or C400. Maybe validation was limited because
we can quickly prototypes, and this quick prototype, because with this new method that he introduced, you can do it quickly, and then we can see quickly whether we can beat whether we can improve the accuracy even further of get it more than 85 for that new MNIST. So that was quite different topics, but I feel that there is some excitement here. Yeah. So first is how to visualize, how to represent your final knowledge, because finally, when you have again hundreds or thousands of rules, somehow you need to compact them, yeah, and then present them. And one of the approaches, use this heat map, or maybe anyway. So we do need something to post process. And another one is introducing this deep learning. Actually, it's not very deep, 2-layer, but it jump your accuracy dramatically. Right.
Your parallelization at the close level, for 2 layers. I wonder what you may have. I remember you had the drop of accuracy.
But what is beauty also of this approach that you can consider the pool of Tsetlin automaton as a shared resources. Yeah, so you can use it for the first layer TM, and then you can reuse it for the second layer TM, because you sort of you train, you freeze, and then because you freeze, you no longer need them, so they can be reused in the second layer TM for tuning, and then so it's also saving you. So it's saving resources and then give you some promising results. So thanks a lot.
Yes, let's applaud. Yes.
We have one question.
Yes, one question. Yes. Yes.
Hi. So just to confirm, so let's say you have 1568 as a number of literals input in the first layer. The second layer, let's say you have 100 clauses per class, so overall 1,000 clauses, or maybe 200 clauses per class, or 2,000. So 2,000 is the 2,000 bits are the input to the next.
Yeah.
Okay.
But you can, for the second layer, you can experiment, and maybe for the second layer you don't need the same 100. Maybe you can use a much higher number. Yeah.
Higher, basically.
Yeah. Or higher, or maybe lower. Because with the MNIST dataset, you have 780 or 68 features. So if you double them, because you need to neglection, so it's almost 2,000. If you have 100 of clauses, so it means that you are
Sorry, how do you structure then TAs? Because you've got your TAs are even a product of literal by clauses. So now, if you had, say, 1,500 in the first layer, that was one kind of product. Here it was a different one.
Yep, but
you restructure them.
So if we have a chip, when we have a sort of a universal resource of a pool of TA, so for this TM you can use half of them. For that TM you can use 90% of them. So, but this is a shared resources.
Great. So this will conclude this session on demos and tutorials. And now I guess I leave it to Rishad to continue, maybe.